Thank you for inviting me and for coming along to this talk this afternoon. Huge numbers of very different species coexist on Earth, and they interact in remarkably intricate and complex ways. Given that this is the case, how can self-respecting theoretical ecologists bring themselves to study ecological neutral theory? The theory that assumes all individuals are ecologically equivalent, and so seemingly ignores all of that marvellous complexity that we know exists. Here are some example comments about ecological neutral theory. These are real quotes. This flies in the face of years of ecological theory, supported by data maintaining that species are not ecologically equivalent, and preoccupation with neutral theory could marginalise biodiversity science, competing for resources with process-based studies while having little to offer conservation and policy. And finally, it's probably the most misunderstood theory in contemporary ecology. And it's with these kind of comments in mind that I want to talk to you today about ecological neutral theory and answer the question, is it madness or simply misunderstood? And as part of that, I'm going to be talking to you about prediction of spatial biodiversity patterns with neutral theory and macroevolutionary predictions of the theory. And then near the end, I'm going to show you some of my latest ideas about nearly neutral theory in macroevolution. And finally, the surprise element is a little bit on phylogenetic tree visualization. But first, is it madness or misunderstood? Well, I have to start with a few words about theory in general. In physics, a scientific theory conforms with empirical data and puts forward an explanation for observed phenomena. For example, apples falling to the ground, that's an observed phenomenon. Planets orbit the sun in ellipses, that's an observed phenomenon, and they are so neatly and beautifully explained by Newton's law of universal gravitation. Okay, that's in physics. Now, what about theory in ecology? Well, comparatively speaking, it's a mess. As far as I can tell, theory in ecology is any study that uses formulas or a computer. So if you're engaged in something that isn't in the field or a lab, then you are by definition doing theory or working on theory. And in that context, oh, are we losing the edge of the slide there? That's a shame. In that context, ecological neutral theory is theory, but it is not a theory in the way that Newton's law of gravitation is. So, ecological neutral theory, by the definition that I would prefer to use, assumes that the properties of an individual organism in the system are independent of its species identity. That's the key. It is not the same as assuming all species are identical, because species can have different abundances in these neutral theories. They can be rare or common. It's not just the same as the contents of Hubble's 2001 book on the subject, although that was, of course, the fantastic work that spawned all of the modern interest of the subject. It's not just a single model either. It's a whole suite of models which make this same assumption. And it's not just a term that we can use willy-nilly to mean null model in any context whatsoever. But more importantly than all this, it is not the claim that individuals really are ecologically equivalent. It's just about making some assumptions and seeing where they get us. And that is a fundamental part of deductive science that's common to many other fields. I think the statistician George Box put this very nicely in his now famous quote, essentially, all models are wrong, but some are useful. So what are the uses of this ecological neutral theory then? Well, one of those uses is, of course, as a null model. That's the least controversial use, and that's perhaps why there is some confusion that neutral theory and null model are just these interchangeable terms. To use neutral theory as a null model, you attempt to fit some neutral model to empirical data, and if it doesn't fit the data, then you learn something interesting. You learn that the model doesn't contain all the important points that you need, and that enables you to then build on the model and accept a model that includes some other processes, which is interesting, or to just reject it and accept some alternative hypothesis. If the model does fit the data, then get better data, because we know the world isn't neutral, so the only reason the model can really fit the data is because you don't have enough information. But that is still interesting, and it's quite disarming, actually, how remarkably this simple neutral model can fit patterns which were previously and so easily ascribed to much more complicated ecological mechanisms. The second and more controversial use is as an approximation. And the argument goes something like this. If the model fits the data of interest, whether or not the mechanisms are totally correct or not is irrelevant. The point is the model fits the data of interest and works as an approximation. Then you might as well use it as such, because it is a simple and very easy to simulate and use model. So before I tell you the third use, I'm just going to give you an example neutral model. This is the very most simple neutral model imaginable. Runs like this. You have a number of individuals, in this case they are trees. They would have to be from one trophic level or one ecological guild. In each time step, one of them dies. That leaves a gap that is going to be replaced by the maturing offspring of another individual in the system, which is in this case chosen at random, according to a uniform distribution. And then occasionally, speciation occurs, so a new species arrives in the system, like so. That's the simplest neutral model, but there are many other neutral models, of course, that we could study, and that is the third use of ecological neutral theory as a foundation on which to build more complex ideas from a simple foundation that we understand very well in terms of its theoretical behaviour. So in what ways might we like to enhance this very simple neutral model that I just showed you? Well, one of the ways is to make it more complex and more inclusive of process, but whilst keeping it as a neutral model. So that's what I would call relaxing the auxiliary assumptions of a neutral model, changing things about it other than the fact that it's neutral. And a big category of those is to do with spatial structure. So that example I showed you, that was just everything was well mixed in space. But you could instead have a spatially implicit structure, where you've got, as it would be called in this context, a large meta-community and then a small local community with some dispersal in between. Increasing the complexity, you could have a network of patches, that within each patch everything is well mixed, or you could go fully spatially explicit and have the XY coordinates of each individual actually taken into account in the model and have some kind of probability distribution known as a dispersal kernel to indicate the probability of dispersal over certain distances. The second general category of relaxing these auxiliary assumptions of the model is the way speciation happens. Now remember, in that simple example, new species just zapped into the system as singletons. Another way is to have random fission speciation, where new species arrive by one species splitting into two separate populations. A bit like if I was to draw a line down this room and announce that everyone on this side is now a different species than everyone on that side. That's random fission speciation. Protracted speciation is different from these in the sense that it models the fact that speciation is a gradual process. And that actually makes a big difference, even in these phenomenological models. So you start with what would be called an incipient species. It's the seed of a species, but it's not a good species yet. And then as time passes, it becomes a good species. And then finally, of course, we can use neutral theory as a foundation to build things which aren't neutral. For example, you could take into account different habitat preferences, different body sizes, or you could do something that's nearly neutral, which I'm going to be discussing briefly later on this afternoon. In an analogy, I like to think of neutral theory as being a bit like the dry, tasteless cracker, which is necessary to appreciate the variety of different cheeses that are the more complicated ecological mechanisms that are out there. But without the cracker, you can't really appreciate these in isolation. So with neutral theory, you can say, well, what does dispersal limitation do on its own, without other more complicated theory added, what does it do against this dry background of a purely neutral model? And you find that on its own it does an awful lot of very interesting things, as we will see. So given all of this, why are people arguing about neutral theory? Why do people think it's madness? Well, a lot of the arguments are rather predictably saying, well, the world is not neutral. For example, periodically we get really high impact publications saying, well, we found this data which isn't neutral and therefore neutral theory is rubbish. What do I have to say about that? Well, I agree. Well, not that neutral theory is rubbish, but just that that data might show the world is not neutral, because the world isn't neutral. But just a word of caution, let's reject the theory for the right reasons and not the wrong reasons. And in fact, neutral theorists have a habit of, when they see papers like this, finding a way to get neutral theory to fit that data after all, which in fact is what happened with both of these publications. In the case of the latter one, the Rickless and Renner paper last year, they were looking at correlations in the number of individuals per family and the number of species per family across continents. And they found undeniable correlations across these continents. And they argued that under neutral theory, things would have happened independently in those different continents and you should not have correlations. Therefore, neutral theory is wrong. However, it turns out that if correlations exist millions of years ago when the continents were all messed up, then under neutral theory, strictly speaking, it's possible for those correlations to just persist, because it takes so long for them to relax to the independent state that they will inevitably get to. So, in a sense, that's a bit of a technicality, but it does show that we have to be very careful to collect together this data to really show undeniably that we have some data that disproves neutral theory. So for me, the real issues that are behind the debate about neutral theory are three things. Firstly, the link between pattern and processes, what we see and what's really going on at the fundamental level. Secondly, and less talked of, is the difference between two philosophical approaches, one of which is realism and one of which is instrumentalism. Realism means that you think a model is useful if and only if it reflects reality. And instrumentalism says that a model being useful is not necessarily meaning that it reflects reality. So those, the usefulness and it reflecting real processes become decoupled. So this is almost a bit like politics. Neither of those views are necessarily right and wrong. They are just different perspectives on science and on modelling, which I think play out in terms of whether or not people like neutral theory. And the third real issue is a trade-off between simplicity and complexity in models. Because of course, the more realistic we make a model, the more we have to add to it, the more difficult it is to actually do things with it. And in the extreme case, you've created a monster that you understand no more about than we understand about the real world. And we have to be very careful of that. So, in conclusion of this part of the talk, is it madness or misunderstood? I would claim it's misunderstood. So now let's move on to talk about some of the predictions that neutral theory makes and some of the more applied benefits there might be of that. So first I'd like to talk about the spatial biodiversity patterns, and perhaps the best known of all of these is the species-area relationship. The relationship between an area of land and the number of species observed in that area. And is frequently plotted on logarithmic axis, so log area against log number of species, and typically you get a straight line, which is mathematically corresponding to a power law. At smaller scales, however, generally this curves downwards a bit, and at the larger scales it generally curves upwards. So you end up with these three phases, a triphasic species area curve. I have always claimed, and not yet been contradicted, that ecological neutral theory, in its spatially explicit form, with dispersal limitation, is the only fully quantitative mechanistic explanation for this complete triphasic curve. And those are the predictions of ecological neutral theory. You can see those triphasic curves clearly coming out of it. Moving quickly on, I wanted to also talk about this other piece of work, which was by Storch et al., came out last year. And this is to do with species area relationships too. It's essentially the same pattern. But what they have shown is that across 5 different continents and 3 different groups, amphibians, mammals and birds, you get essentially the same shape of species area curve, provided that you look at area not in terms of kilometres, because what does a kilometre mean to a frog? Nothing. It only means something to us. You measure it instead in terms of the range of species, and then you get this generic universal pattern out. And an even more general equivalent of this, in fact, just naturally comes out of spatially explicit neutral theory. So if we look at what would be called the multi-scale species abundance distribution, so what this is the number of species that you have with different abundances in your survey area, which could be large or could be small. So it's a multi-dimensional object that we're looking at. And what we have there on this graph, on the x-axis, is the abundance of a species. And that says abundance class because that's a commonly used way of drawing abundance distributions. It's essentially like taking log to the base 2 of the abundance of a species. And on the y-axis, you've got the proportion of species with that abundance. Sorry for those of you who probably already are familiar with this. But when you take, so all of those curves there, they correspond to a fixed ratio of sample area to mean geographic range of a species in a neutral model. And you always get, if you scale them onto one another, so you're not changing the shape of those curves, you're just squashing them and moving them, you find that they are in fact all fundamentally the same shape. So you get the same shape of species abundance distribution when out of neutral theory, provided that you are sampling from the same ratio of area to mean geographic range of a species. And if you change that parameter, sample area, to mean geographic range of a species, you get a range of different shapes, going from the famous log series all the way through to a much more peaked distribution for species abundances. And that suggests, at least speculatively, the possibility that there might be a universal pattern in the multi-scale species abundance distribution as a further generalisation of what Storch et al. Found. So I'm now going to move on from the spatial patterns to talk a little bit about the macroevolutionary patterns that come out of ecological neutral theory. Of course, they do make macroevolutionary predictions because the theory contains or can contain speciation. As soon as you've got that, macroevolutionary patterns of some form will emerge. The question is whether they're at all useful or interesting. And I'm going to start by talking about islands because I think islands provide a really great testing ground for understanding and studying macroevolutionary patterns. And you can't talk about modelling on islands without first winding back to McArthur and Wilson's seminal work, their theory of island biogeography. And in that theory, they envisage a dynamic equilibrium between immigration and local extinction on an island. So the total species richness on an island stays approximately constant over time, whilst the species themselves are in a constant state of flux, with new species coming in and then other species becoming locally extinct. This concept was, to some degree, extended to create the unified neutral theory of biodiversity and biogeography, which was the start of the studying of really modern neutral theory in ecology and evolution. And in that, we're not looking at species, we're looking at individuals. So it's not species that arrive on the island, it's individual organisms that, of course, belong to a species. And furthermore, you are looking at what's going on the mainland. On the mainland, you have another dynamic equilibrium between speciation and extinction. That to really have the rich behaviour of evolution on islands, you must also have in situ speciation on islands, which is something that I added for this study. And the speciation on islands is done with protracted speciation. Remember me mentioning earlier, that's where speciation takes time rather than being instantaneous. And the amount of time that speciation takes to complete once it's started, in this case, was linked implicitly to gene flow. It linked implicitly to that dispersal between the population on the mainland and that on the island. And with that, we were able to study the richness of species that were immigrants on the island, so they also appear on the mainland, the same species, and those which are endemic on the island. So this is results we get from that model. On the x-axis of this graph, we have the area of an island, and on the y-axis is the level of isolation from the mainland. And these colours, the yellows correspond to the largest number of species, and the black corresponds to no species at all. So this is showing the number of species that arose through immigration. And you can see that the largest areas of island that are closest to the mainland have the largest number of immigrant species on the island. The endemic species show quite a different pattern, and they are in fact further split into two types. The anagenetic endemics are those which are endemic to the island, but their sister species is on the mainland. And with those, you see them, most of them, on the largest islands that are of intermediate distance away from the mainland. And the cladogenetic endemic species, these are the ones that are endemic only to the island, but their sister species are also on the island. And therefore, you're probably in the scenario like Hawaii, where you've got large clades of endemic species that evolve in situ on the islands or archipelagos. So these patterns are qualitatively in agreement with empirical data of island avifauna. Here you can see that the larger islands that are nearest to the mainland have the most immigrant species. The larger islands that are an intermediate distance away have the most anagenetic species, and the larger that have the most, the larger that are furthest away have the most cladogenetic species. So in agreement with the model. Another prediction the model makes that we weren't able to test due to general lack of data is that, of course, it's an individual-based model. And so it doesn't just make predictions about numbers of species, it makes predictions about those abundances, whether those species are common or rare. And this is an abundance distribution like the one I described before. X-axis is log to the base 2 of the abundance of a species, and y-axis is the number of species. And those black lines are showing the abundance distribution on the mainland from which things are immigrating to the island. Whereas the red is showing the immigrant species. And it looks as though that's just been shifted to one side, to the left there. And that is because for an island that's really close to the mainland, you're essentially just sampling from the mainland and you don't get any endemic species at all. As you increase the distance from the mainland, the abundances of species on the island start to decouple from the abundances on the mainland. And then, those green bars starting to appear, those are the anagenetic species. So, as isolation increases more, we see anagenetic species appearing. And then, the blue, those are the cladogenetic endemic species. And what's really notable is that this is showing, at least in the model, that the most abundant species on the islands where there are endemics should be the endemic species. Now, many would argue that is not observed, and I would say that's probably because of human influence, which of course isn't in the model. But indeed, although there's not much empirical data, I did find a study of Borges et al. Which showed that in the untouched, pristine native habitat, the endemics are indeed really common. In the altered habitat, things are of course different. But anyway, just continuing to the pattern to increase isolation of the island still further, eventually we reach the scenario where almost everything on the island has an independent evolution and there's hardly anything present that's also on the mainland, or even that has a sister species on the mainland. Which brings me on to the second macroevolutionary pattern that I want to discuss for the rest of the talk, and that is phylogenies. So, phylogenies are typically modelled in the field by the birth-death model of diversification. And that is a lineage-based model. It's not individual based, like ecological neutral theory is. And each lineage has an equal probability of going extinct or of speciating to make two lineages. Once you have that in the model, you're able to predict the shape of phylogenies. But neutral theory, of the kind that I've been discussing, is individual based. So it's not looking at lineages, it's going within them, it's looking at individuals. And the real world is individual based, not lineage based. So you would think that based on that alone, it should be better. But also, it can perhaps help linking with ecology, because neutral theory is individual based, and so it naturally makes predictions about a species' commonness and rarity, abundances and other ecological factors that perhaps would have to be forced into the birth-death model of diversification, which isn't individual based. But does the neutral model do a good job of fitting phylogenies? Well, some of the patterns of a phylogeny can be viewed in terms of the balance of a phylogeny. And the easiest way to describe it is to say, this is a very balanced tree, and this is a very unbalanced tree. And just to give you a sneak preview of the very last thing I will show you today, in the phylogenetic tree visualizer I'm going to be discussing, that is how a very balanced tree looks, and that is how a very unbalanced tree looks. But we'll see more of that later. The point right now is that ecological neutral theory, as shown by David et al., does produce more unbalanced trees than does the birth-death model. And also that real phylogenies are more unbalanced than the birth-death model predicts. So ecological neutral theory, in that sense, of balance, does a much better job than the birth-death model of predicting phylogenies. But then there's the other side of the coin, which is the rate of diversification in phylogenies, and that is still a problem with ecological neutral theory. It doesn't do a good job at all there. And to illustrate that, I'm going to show you a lineages through time plot. This is, I think, the best way of really picturing diversification through time. On the x-axis we have time, before the present, and on the y-axis we have the number of lineages in our phylogeny, which starts at 1, and the outside 2, depending on how you look at it. And then, as time passes, your phylogeny has a larger number of surviving lineages, and so this curves upwards. But notice that the y-axis is already a logarithmic scale, and still the number of lineages in this phylogeny is curving upwards. So this is a much faster than exponential rate of accumulation of lineages. And by comparison, the birth-death model is much more of a straight line, with just a little upturn at the end on the same axes. Whereas real data, in contrast to both of these, more often than not tends to actually curve downwards rather than upwards. That's known as a slowdown in diversification. So really, the birth-death model is wrong here, but the neutral model is really much worse still. It's truly egregious in terms of its lineages through time plots. So how can that be fixed? Well, of course, this idea of protracted speciation can help, because really near the present day, protracted speciation says you can't have speciation that happened 5 days ago, because speciation is a process. So if it started 5 days ago, it wouldn't have finished now. But unfortunately, that's not enough, because it just chops a little bit of that peak off. But still, the overall shape of this is to curve upwards, even in logarithmic space. And that's not, as a rule, what's observed. And even if that is sometimes observed, the point is this is what you always get with these neutral models, and there seems to be very little way to get away from that. That's where the protracted speciation cut off the tip there. The only possibility that I was able to find that might perhaps work is to have an increasing meta-community size. And that means that the number of individuals in your system is exploding, then you can get a much straighter and more reasonable phylogeny. But still, it's not that acceptable as an explanation, because we shouldn't need a general model of phylogenies to require the number of individuals in the system to be always increasing dramatically. And so I'm inclined to go as far as to say that ecological neutral theory may be good for fairly recent time, but once you get into deep time predictions, it can't make good predictions of the phylogenies. And I would suggest that a potential solution to this, or potential fix, is to move away from neutral theory and towards something built out of it, which is nearly neutral theory. So, the reason why I think this is an appealing idea, to have a nearly neutral theory of macroevolution and phylogenies, is because there is already a nearly neutral theory of molecular evolution. And in fact, if you look at the history of it, there are big arguments about the neutral theory of molecular evolution, and very much the same kind of thing happened, and eventually people realised that nobody believed it was real, it was just a model, and then along came nearly neutral theory and solved many of the problems. It involved allowing slight increases or decreases in fitness of individuals. And it fixed a lot of the problems, particularly in terms of the time scales of those models. We've got all kinds of noises going on there. I wasn't expecting to hear the siren. Also, most notably, it indicated a relationship between the size of a population and the rate of evolution. So for all these reasons, I think it's quite exciting to translate those concepts through into neutral theory of macroevolution and biodiversity. So translating them to a multi-species community scenario. And this is the model that I simulated for that. So I'm demonstrating it with a very simple example. 6 individuals, and the shape corresponds to species there. You get death in each time step, and that leaves a gap to be filled with the reproduction of another individual. And under classic neutral theory, all of those 5 individuals that could potentially reproduce to fill that gap have an equal probability of filling the gap, so they all have an equal fitness. But under nearly neutral theory, you have different fitness categories, and there's a very, very slight difference in the fitness, and therefore a very, very slight difference in the probabilities of those different ones to fill that gap. And in this instance, I used the solid black colouring to indicate the highest fitness, the grey to indicate intermediate, and then the outline to indicate the lowest fitness. So S is quite a small number, but it's still there. And then to finish off the description of this model, you have the possibility occasionally of speciation occurring. And when that happens, the new species may have a slightly higher fitness or a slightly lower fitness than the one from which it evolved. So that's the model. It's still quite simple. And these are the predictions that come out of it. So I'm going to show you first the predictions you come out for the case where S equals 0. So this is actually the predictions for a pure neutral model again. This is that lineages through time plot, accelerating upwards in this unrealistic way, you remember me showing before? And these two show the species abundance distribution in 2 different ways. In terms of the abundance plot, in octaves, like I've shown you before, that's essentially log to the base 2 abundance on the x-axis. And in the middle there, you've got rank in abundance on the x-axis, so you've ordered them all according to the most abundant, and then you've plotted that against the log of their abundance. So that's what you get with a neutral model. In the case where S equals 0.0001, so that's 1% of 1% fitness advantage by being lucky and speciating in a positive way, you get hardly any difference, but it's still almost noticeable on the lineages through time plot. By the time S equals 0.01, that's a 1% fitness advantage on speciation if you're lucky and go the right way rather than the wrong way. So that's almost nothing ecologically speaking. It would be very hard to detect if a species was just 1% fitter than another. I think you need a lot of data to really prove that, but yet it makes such a huge difference here to the predictions, particularly in terms of the lineages through time plot, which now looks very much like the lineages through time plot of a birth-death model. And at the same time, the abundance distributions don't look that much different. They still look rather like the log series distribution that we had before. However, what you in fact have is a greater number of really common species. And that, if anything, is better than the earlier neutral theory, which failed to predict the existence of these really common species which we know exist. Whereas nearly neutral theory can predict their existence because they are marginally fitter and have been around for a long time, and so they can get to be really common in that scenario. If we look at the crown age of the phylogenies, so that is the age of the most recent common ancestor of all of the individuals in the guild that we're looking at, as you go from neutral to nearly neutral, you start to see things converging to common ancestor much sooner, and perhaps unrealistically soon. But this was for a very small example of just 100,000 individuals. In reality, you're going to have maybe 1 billion or more individuals easily, and so you're going to be multiplying up these figures by several orders of magnitude. So I don't think it's too bad. The last actual result I want to show you from the nearly neutral theory is this graph showing the relative fitness weights of species. So on the x-axis, we've got the fitness. You can see some of them have a fitness of 1 compared to the others, and others, the most fit one, has a fitness of 1 plus s to the power 17. But remember, s is still very small. And you've got this very peaked distribution. So this is not actually so far away from being a neutral model. What you find, in fact, is if I can just turn that into a cartoon, you've got this distribution of fitness weights, and as time passes, it moves. And it moves because there's this gradual progression of things getting fitter. That doesn't mean that they're fitter compared to each other, because of course what matters ecologically is that something is fit compared to what else is alive at the time. But it does mean fitter compared to their ancestors, perhaps in response to a changing environment, or perhaps there's been some actual progress happening. So for this species here, at time 1 it's comparatively fit, but then at time 2, without changing at all, it's not so fit anymore. So there's a natural life cycle of a species occurs in this scenario. The probability of reproduction, the distribution over different species, remains constant, because although this shape is moving to the right all the time, it is still the same shape. However, for a species, your fitness starts off on the right-hand side of that distribution, and then you end up on the left. And what this is showing is the relationship between the size of a community and the rate of evolution in that community. And you see that as the community gets bigger, you have a much faster rate of increasing fitness in that community, a much faster rate of evolution. That is analogous to the result you get in the population genetics. And the implications of this are, I think, quite interesting. For example, in the case of invasive species, here we have an island and a mainland, and the fitness of everything is equal at this point. And then if we run time forwards, the island, if it's fairly isolated, will, because it's a smaller population, the rate of evolutionary progress will be slower there, naturally as an emergent behaviour of this model, compared to the mainland, which is a very large area, so evolution and evolutionary progress will happen faster. And then eventually you'll end up with a scenario where the things on the mainland aren't actually better than the things on the island, and therefore they will invade much more easily. And that's really the final speculative word on this that I have to say, is just that we started off with ecological neutral theory, which was this idea, although we know it's wrong, that all species and all individuals rather are ecologically equivalent, and set that against a niche-based view that they're all different, they all fit in its own niche. But part of that is also seems to be that, yeah, they all have their own niche, but overall it's not that one is just better than another, they're just different, not better. Almost like a sort of socialist view of the way that species are. And actually, in the case of species, I'm not sure I quite buy that argument. And that's what nearly neutral theory says, that actually, in a small way, some are better than others. And take this for example. So this a beautiful animal, as you can see, the Indian peafowl, or peacock in this case. We all know why he is increasing his fitness with this amazing display. So that's fine. But what about this species and the niche it fills? what stops another species from filling that niche? Another species that doesn't bother with all of this crazy, expensive sexual selection. Now, there could be several explanations for that, and one of them involves the idea that actually they have a genuine benefit by having that. It enables positive mutations to travel faster through the population. But it could also be that they used to be comparatively fit, they used to be better, and they wasted their advantage on crazy sexual selection. Or it could be that they weren't any fitter and they have now committed evolutionary suicide by doing this. But that's just something speculative to think about. So in conclusion, neutral theory is useful as a null model, as an approximation, and as a foundation on which to build more complex ideas. Neutral theory of protracted speciation can make rich and macroevolutionary predictions, including of phylogenies. But I think that nearly neutral theory will be needed to make good predictions over deeper timescales, starting from the starting point of ecological neutral theory. So we all know the world isn't neutral, but could it be nearly neutral? And finally, this is a very short bit at the end, phylogenetic tree visualization. And I realise that I've not got much time left, but I'll keep this quick. This is really quite different, and it has to do with the tree of life. It has millions of leaves, and each is a species about which we know huge amounts of information. It has millions of branches, and each of those tells an amazing story about evolution. So there's all this information out there, and all of our research and areas of study, in fact all of biology, can be pinned somewhere on this tree of life. It's like the map of all that we know, in a way. But what interests me is how can we visualise this tree of life? And this is the kind of way that people seem to have been doing it, with these classic cladogram views, sometimes twisted around a circle, sometimes flat. But the problems I have with this is that you can't show really large amounts of data. You can't show metadata, additional information on the leaves or nodes, or at least only very limited metadata. You can't show large amounts of it. And for me, it's not very intuitive either to explore, especially for a large tree. And with the Open Tree of Life project, now building trees with over 1 million species, it's a shame that we have no nice way to look at them afterwards. And finally, I think that as scientists, it's our duty to excite the general public about our field, and the general public won't get excited about this. So then that's a dry scientific diagram. So it's with all this in mind that I wanted to show you OneZoom, which is live and online and just over a year old now, and that is a fractal explorer for the tree of life. So it's a new way of looking at these kind of data. So I'm just going to load it up now. Excuse me. Okay. So, slight adjustments to the screens. This is another where it's probably not going to work for some reason. Aha, right. So, this is OneZoom. That's exactly what you can see on the internet if you go to onezooms.org. And the idea is it's like a map. Everything is on one page. All you have to do is zoom in and out to get that information. So, for example, we can zoom in on mammals. And within them, on placental mammals, and then on primates, and then on apes and humans, and then finally on humans. And you'll notice that we are a green leaf in amongst this sea of red. That's because I've chosen a colouring that indicates the IUCN red list status of conservation for various species. There's also links to Wikipedia there, which I won't click on because I'm not on the internet right now. This is running locally. But you'll see also you can zoom in on interior nodes and see information about the pie charts showing the IUCN red list status, how much phylogenetic diversity there is. And you can perhaps already see how, with this zoom-in concept, you can put limitless information on every node, on every leaf, and you can have the complete tree of life and more, all included. I'm just going to zoom in on birds here. We've got every described bird in here, thanks to the recently published tree by Yates et al. And once you zoom in a long way, it perhaps takes that to really appreciate how the zooming enables us to put so much information in one place. And this is also a very natural way, I think, of visualising large amounts of information, because in real life, that's how our brains have evolved to work. We don't click on a link in real life and zap to somewhere else. Instead, we look left, right, up and down, and we look closer and we look further away, and those are the only 6 things we can do, right? And the whole of the internet and pages and books and all of that is something we've invented to cope with large amounts of information in a way that we are fundamentally not used to, that this concept replicates. And it's done, incidentally, using a technique from mathematics called fractal geometry, which I adapted for this purpose of data visualization. You can also search for species that you're interested in, and you can visualize the tree in different shapes. So this shows the balance of the tree. You can see at a glance where the balanced nodes and the unbalanced nodes are, so you can see straight away that that's unbalanced. Lots of small branches to the left with not many species on, and most of the species going straight ahead. Whereas up here, for example, you can see this is a fairly balanced node, splitting equally from the left and to the right. You can also have a growth animation, which shows how the tree grew through time. It tells you the date at the bottom. It's quite small, you probably can't read. But again, that's another way of showing this information of how phylogenetic tree grew over time. And the final thing I'm going to just show you, and at the same time as that, I will take questions, is tree of bacteria. So, oops. So this is a 408,000 node tree, and I've just searched of bacteria, and I've just searched for one particular species in there. And this really gives you an idea just how big the 408,000 node tree is, and that's already only a fifth of the total size of the complete tree of life, which ultimately one day will be there with photographs, with pictures of fossils, with information, with links to other websites. That's the ultimate goal, the Google Earth of biology. That's what ideally I'd like to create with this. And also exhibitions at museums, places like that where members of the public can go and zoom in on a multi-touch display. That is also all happening as part of this project. So while we're zooming in, I'll be very pleased to take any questions in the last few minutes. Thank you.
Since it's up, how do you deal with the fact that there is no unitary tree of life, given that genes transfer between species, particularly in the microbial world?
Yes. So this particular tree uses the core genome of the bacteria. There's I'm going to show my ignorance here because I didn't build that tree, that came from the literature, but there is a core genome of bacteria where I understand there's not much natural transfer. But what I would like to be able to do, for instance, not so much in bacteria where it's going to be a complete mess, but in plants, to be able to show, for example, once you've gone onto the leaf of once you've gone onto the leaf of a tree, then that's one species. But then around that could be indications of what other species it hybridizes with. So there's no reason why you shouldn't have information on hybrids embedded to be zoomed in on. And there might even be an as yet to be discovered fractal form that enables you to visualize actual networks. I wouldn't rule it out, because especially since, although there will be cross transfer, so it won't be a tree, it will be a net. It will still be a tree-like net. It won't be completely messed up. It will be rather hierarchical. So it might be possible, but at present, all I can think of is to just indicate that information as metadata on the tree. Thank you.
In the neutral materials,
Yes.
there's stuff going on in that process. There's the rate at which populations change locally, ecologically, and then there's the rate at which they change in space, and there's a rate at which speciation happens.
Yes.
Can neutral
sure whether they can tell us a more believable story, but it does have its own story, which is that there are natural timescales and length scales that pop out. So, for example, the natural range of a species in a neutral model turns out to be the dispersal distance divided by the square root of the speciation rate. So that's actually the natural distance of a range. And if you actually square that, then you get the range area rather than the range span. So you do get natural length scales out of the model coming from speciation and dispersal. But I'm not sure whether they would be more believable than other predictions for those, or whether they would just be delicacies for the statistical physicists to enjoy. Yeah. Sorry, that's quite a weak answer, but hopefully it helps.
Yeah. So let us ask about the island biodiversity part of what you were talking about. Much of that is in the sort of context of species colonising islands from the mainland and the patterns that you see. So do you come to different conclusions if you assume your island has been formed from a continuous patch of habitat and has then become an island? So it's all been driven by extinction really rather than colonisation. Sort of thinking about, you know, those sort of cookie cutter and habitats and things like that.
Very interesting question, and it's a shame that I actually cut some slides on this, but I can tell you briefly. So I actually studied the approach to equilibrium in a neutral model from a volcanic origin, where you've got the sterilized island that just appears, and for land bridge origin, which is what you're talking about, where you start off with just a sample from the mainland, and then because you're isolated, you're going to naturally drift. So under the neutral model, it doesn't matter which of those you start on, you end up in the same place, which depends on your area and level of isolation. Of course, in practice, if you're a land bridge, then you're probably not going to be stupidly isolated very soon, just because you've got to drift a long way as a land bridge to get as far away as Hawaii is. But if you ignore that, it would predict that just the isolation and the area give you the equilibrium situation. But on the approach to equilibrium, of course, it matters very much where you've come from. And in fact, maybe if I've got time, I'll show you very quickly one interesting graph about this. I do have to just try it. So, quickly, you can see the very messy contents of my computer. So, this is the... Okay. Aha. Right. So, that right there is, on the x-axis, species richness, and on the y-axis is rate of either either immigration or extinction. And that graph right in the middle, if I just wind back, that graph right there, that is what you get when you're at equilibrium and drifting a bit to either side of it. That is like the classic MacArthur-Wilson relationship between immigration and local extinction. But that is actually the emergent behaviour of an individual base neutral model. That is not the input from MacArthur-Wilson model. But that's at equilibrium. An approach to equilibrium from volcanic origin, you get that. And an approach from land bridge origin, you get that. So overall, you in fact get this very interesting and, I have to say, unexpected behaviour with a non-monotonic rate of extinction and immigration, and with quite unusual little tweaks in the middle. And I've cited Bush and Whitaker there because they did actually observe non-monotonic immigration and extinction rates, although they attribute it to other reasons. This shows that actually neutral models do not just predict that, they predict quite rich behaviour as emergent behaviour in terms of these classic MacArthur-Wilson plots of immigration and extinction. And that all depends on these scenarios that you brought up of where you're approaching equilibrium from.
Okay, it's almost 2 o'clock, so we should probably wrap up. Just give my lecture to go to. Thanks very much, James. Well done for coping so well with all the